So what we do is find the deflection between 1 and 4 for the structure A, and then we can think about applying for doing that we can think about applying a 1 Newton force, a virtual force along 1, 4. We can potentially recalculate all the forces, but then we'll notice that since this is the same type of force that we applied before, we can use the P sub 1 Ni that we previously calculated. So what that means is, if I want to calculate the virtual work in the presence of both the external force, the P times P sub 1 Newton as well, this is the formula that we get. Essentially, this is the deformation. So this part from here to here is a deformation. This is the virtual force that we apply, and since the summation is going to be the total virtual work. Since we have removed the link 1, 4, we basically say I not equal to 1, 4. Now what we do is, we know that if you do the same thing for this link, if we apply P times 1 Newton here, the deformation is going to be P times 1 Newton times L divided by AI, EI. We set delta 1, 4 times 1 Newton plus delta sub B 1, 4 times 1 Newton equal to 0. Essentially, we're doing this because we are applying forces which are equal in magnitude but opposite in signs, and hence the deflection that we calculate along the forces need to be equal in magnitude but opposite in sign, which basically means that the sum of the two values needs to be equal to 0. Next, we're going to define two work terms, We'll call the summation of P sub EI, P sub 1 Ni times Li divided by AI EI, the summation of that. We'll call this PW sub PE P1N. So this kind of corresponds to the cross product between the internal forces resulting from the PE, which is the external force, and the 1 Newton force applied along 1, 4. So that will be this term. So this will correspond to our work. This here, W sub P1N, this would basically correspond to applying a real 1 Newton force between 1 and 4 and a virtual 1 Newton force between 1 and 4. So this work would correspond to the product. Since both of these would be the equal magnitude, the internal forces due to the 1 Newton would be equal in magnitude, we basically get a P sub 1 Ni squared. The only thing to note is we set P sub E 1, 4 to 0 and then P sub 1 N 1, 4 to 0, which basically would allow us to just create one summation including all the terms. So how do we get that? So we have this I not equal to 0, and then from here we notice that delta 1, 4 would be basically this 1 Newton squared, and then if we can substitute PE equal to 0, and then we can get rid of this I not equal to 1, 4. Once we do that, going back, we'll end up with this equation over here, and then the way we solve for P is negative this value over here divided by P sub 1N. At this point, I'm going to slide back, and you can pause this video and then try to solve for the redundant truss structure. So this is the redundant truss structure we're actually trying to solve. Hopefully, if you're resuming the video, you've already solved this, and then I'm going to kind of solve these problems with you, and then we can see what is it that we get. The first step is we are going to ignore the 1 Newton force along 1, 4. And then we do the vertical equilibrium and the horizontal equilibrium and moment equilibrium for the whole structure, which will basically give me F1y is 10 newtons, F5x should be minus 20, and then F1x is 20 newtons. Next, we'll use method of joints. Taking equilibrium for joint 1, we find this T12 is minus 20, T15 is minus 10. Similarly, we do moment equilibrium about joint 3, and then we do moment equilibrium the equilibrium for joint 2 and equilibrium for joint 4, and then we can get these particular values. You can just double check to make sure you got these numbers. The next thing we do is to calculate the P sub VI. This should read VI. So we're going to basically calculate P sub Vi, which is the internal force due to just the 1 Newton force along this direction. So you'll notice that potentially using either the method of sections or kind of just doing the equilibrium, that if we are completely to either the left or the right of the two 1 Newton force that we are applying, the forces will be completely zero. So essentially, if I want to calculate that, I can take kind of the section, this section of the truss, and then I can calculate, since there's no external force over here, this force needs to be zero. Alternately, if you consider this part of the truss structure, I'll take moment about joint 1, and then I notice that both this 1 Newton and this 1 Newton passes through this point. So any external support force needs to be zero. Same thing if I take moment about 4, I'll find that T23 is 0. So whatever which way you do, you'll actually find T23 and 3,4 are equal to 0. Then we again do the joint equilibrium. We do the X and Y equilibrium for joint 1, and then we find, similarly doing for J4, we find these values for the internal truss forces due to the 1 Newton force. Next step is we kind of put a table for all of these. Calculate, put in the length, put in the internal forces, put in the 1 Newton force, calculate the work done for each of those. So this will basically be this times this times this. Actually, I'm missing the AE term here. All of these will be divided by AE. And then once I do that, I can find the ratio between this and this. That will give me P is minus 8.54. So this will be the force in the redundant truss structure. And then using this particular value, I can actually calculate, okay, I have the AE over here. I can calculate the total force, which is going to be this force plus P times this force. So notice that this is 20, and then 7 times 0.7 times 8.54, and then we'll get this value. And then do this all for all the structures, and then we can get the total internal forces in all the structures. This is including the redundant link that we moved. The next step is we are interested in calculating the deflection of this redundant structure here along the direction of the external forces. One way we do this is to apply an additional virtual force along the external force. This is kind of a little bit annoying because just as we solved for the virtual force, the internal forces using the method of using virtual work, we have to redo the same set of calculations here, which is kind of slightly annoying. We'll do a trick here. So I'm going to assume that I can apply a virtual force which is equal in magnitude to the external force. If I did that, all the internal forces in all of the links would be equal to the total force that I calculated due to the external force alone. Because I'm applying the same magnitude, the structure doesn't really know, it's going to produce the same amount of load. What I can do is basically replace P sub V by P sub E, and then I get this particular equation over here. So this is what you're going to do. Again, use the table before, and then I want you guys to try to solve for this particular value. Essentially, you take this total load and then try to find for deflection. So at this point, you should pause the video, try to solve it yourself. Okay, hopefully you solve these values. So this is the total force. We're going to assume that the link area is 1 centimeter squared. The Young's modulus is 200 gigapascal. Okay, at this point you can pause and then try to solve for the forces. So what do we do? Basically P squared I divided by AE. AE kind of remains here. And then I sum all of these, I get this particular value. And then I can calculate delta 3 comes to 0.507 micrometers along the external force. This basically concludes our presentation on virtual work, and basically using the method of virtual work to calculate both the solution to a redundant structure as well as to calculate the deformation of the end point on which the load is being applied. Thank you.